Okay, this is a great system that we've got with this little challenge and response. But again, it's predicated on a very important assumption that needs to hold. Nominally, that the attacker cannot access the badge binary, or maybe even more specifically, the attacker can never gain access to the fleet key, right? This is one key that goes in every device. If an attacker were to figure out what the value of that key, then essentially our whole system comes down. And we're going to look at a couple of scenarios where now maybe that's the case actually. So maybe they're able to get their hands on a badge and extract the firmware off that badge and then get access to the fleet key. Or maybe they, they use some social engineering. They contact, us or the security company that makes the badge system, and they're able to get that key out of a tech support. Or maybe someone accidentally looks up those, accidentally leaks those credentials into the source control, and they get them that way. However it happens, we're going to need to, we're expanding our threat model to include the possible scenario where the attacker has access to that. And what we want is some way to secure the system from sort of this catastrophic failure of them, the attacker, getting access to the fleet key. So our solution to this is that we're going to provide a way for each badge to have its own unique secret key. And this helps limit what's called the blast radius problem. So with a fleet key that went in every device, the blast radius was huge. If one of those if the fleet key leaked, the whole system came down. In this modification, exercise 3, we're going to give each badge their own unique key. So if an attacker gets access to that key, all they've done is be able to compromise that one singular badge, not the entire system. And we're going to do this by encoding a way for the badge's keys to be derived from information that's known to the reader. All right, so at build time now, the badge will get its device key, and this is computed by computing the HMAC of the fleet key and the badge's identification code. Now notice that the badge itself doesn't get the fleet key at all. All it gets is this device key, which is unique for each badge because they all have unique IDs. The reader, in turn, gets the fleet key. And so in the process of unlocking, the badge provides its UID to say, hey, I'd like to unlock. The reader provides the nonce just like before, and at the same time computes what must be the badge's key if it's a valid badge, using the same construction that was used at build time to put that key in the badge. It's going to compute the HMAC of the fleet key that the reader has and the UID that the badge just provided to get what must be its key. The badge, if it's valid, will compute the HMAC of that nonce using its device key, just like before. And the reader can then check that that value matches what it should get by performing the same computation using the device key that it just derived. And so in this fashion, the reader can sort of compute device keys on the fly, and it doesn't have to store thousands of keys for different badges. And each badge only ever sees its one unique key. So again, if we have to, account for this scenario where we don't want the exposure of one key to kind of bring down the whole system, each badge has its own unique key. And so the exposure of the one badge key only, makes that one badge vulnerable, not the whole system. Now, I want to mention that this really brings to our attention the importance of key management. And key management has been important the whole time, but now it's really important because we have multiple keys kind of in use at the same time. And I just want to mention that we're not really going to there's not a ton of exercises that related to this today, but this is another part to the security question. It's easy to secure, the transaction between the badge and the reader. And if we're not properly managing our keys, we just give an attacker another route into our system. And so if we are thinking of this very holistically, we have to ask ourselves questions like, how are these keys being generated during the manufacturing process? Where are they being stored so that we make sure that no two badges get the same key? How are they being stored on the badge or on the reader? Is there like a special hardware security module where they're being stored that helps prevent key exposure via certain physical attacks? Additionally, we might ask, well, how are these keys rotated or revoked, right? We have to think of the entire kind of key life cycle, which includes, a badge coming back to us and getting scrubbed, or maybe someone says they lost their badge, so we have to revoke a key from use. These are all important questions ultimately to think through when you're analyzing the security of this system that go beyond just the tangible process of two things authenticating each other. But those are exercises for a different workshop. Okay, so we're going to get into exercise 3 now, where we see this process in play. One note is that if you try to run the tests on exercise 3, you're going to get an error. And the reason is because I'm slowly taking away some of the scaffolding here. The first exercise in the red level asks, do we understand kind of what this helper function derive key is doing? So this is the step where we, like in the diagrams you saw, where we are computing, the key based on a fleet key and a UID. So quick question on kind of how that operates. And then before you can run the tests here, there are 2 blank lines in reader.py that you need to fill in, where the badge key is computed using derive key, and then the expected value from an authentic badge is computed using the HMAC algorithm, that badge key that we just derived, and some other data. So fill in those 2 lines first, then you can run the tests. As long as they're correct, you should see 100% of the tests passing. And the last exercise here in the red level is to draw the flow chart of what the present function is doing, so we can kind of see how the sequence diagram in the notes maps to the code that's presented in the exercise. And then, of course, I'd encourage you to pick one or more of the yellow and green exercises to deepen your understanding before you move on to the next video.